Today I'm going to show you how to use the Arduino as an oscilloscope using a potentiometer to control the sample rate. We use the Oscope as a function generator so that we can take readings from the Arduino.
What you can see in the VESA monitor on the bottom left is the frequency changing depending on the position of the potentiometer I just showed you. I can go down to a sample rate of just 1 Hertz and go up to a sample rate of 600 Hertz, although it's trivial to change in my code that I will show you later to change what the maximum sample rate is. But as you can see, it changes depending on the position of that potentiometer. It's also a completely analog scale, which means I can go anywhere in between there. So I can very closely fine tune what the frequency is to exactly 500 Hertz, as you'll see for the lab. And it's very accurate and very stable. It rarely changes more than about 1 Hertz. Before we can understand the code, we need to understand what we're trying to achieve. In this instance, we're trying to take the input of our function generator here and sample it using the Arduino. But we want to take different sample frequencies, and the way we control that is using a potentiometer that is read by the Arduino. This is then sent from the Arduino over serial to processing. Processing will then not only plot it, but it will also do the fast Fourier transform, and it will display that as a graphic. The code that we're going to have to write is the code for the Arduino that will not only read this input from the potentiometer, it will then do some math on this reading from the potentiometer and turn it into our frequency that we need to read the function generator at. To get a better understanding of how sampling rate of a frequency input can affect the Aliased frequency, I sampled a number of different frequencies with a number of different sample rates to complete this chart here. Along this diagonal here, half the sampling rate is lower than the frequency input. What this creates is a situation where we have aliasing. One of the most interesting examples of aliasing is when you have 100 Hertz sampling rate and 100 Hertz input frequency. In that situation, the sample is taken at the same part of the waveform every single waveform. But that results in a constant voltage because it's sampling at the same part in the waveform. The way to calculate our perceived frequency, fp, is using f, which is our frequency input, fs, which is our sampling frequency, and the nearest integer function here. I'm going to do it with the example of 142 Hertz for our sampling frequency and 215 for our input frequency. Here you can see it's filled out. The result of our fraction here is 1.51. That gets rounded up to 2, as you can see here. Once you've evaluated this function and taken the absolute value, you get the result of 69 Hertz as your perceived frequency. This is the Aliased frequency. The 16 screenshots showing now are the screenshots of the Oscope software and VESA software that were used to create the data table shown previously. Right here is the code. Let's break this down to figure out how each part of this code works. This is where I'm setting up all my variables. This then brings us into void setup. In void setup, we do the usual things, which are set up serial, set the pin modes to different pins. That go switch does, it's basically a digital pin, and if I pull it to low, then that means that my Arduino is going to read as fast as possible. After setting up all of our pins, we can then look at void loop. Here in void loop there are a couple notable sections. First off, we are checking the potentiometer, and this potentiometer is always read at the same frequency, and I actually have it set to about 5 Hertz. I don't read it faster than 5 Hertz, and the reason being the potentiometer is not going to be changing that much, and I want to spend as little time reading the potentiometer as I can, so I can spend as much time keeping the correct and accurate timing for the actual sampling of the Oscope signal. The second part of this code checks to see if it's time sample from the Oscope. Next we're going to go on to the pot read and scale function. This one, it first checks to see if the go switch is pressed and reading the potentiometer reading, and we're resetting the timer for that. After that's done, we're going to do a simple check to see if the potentiometer's reading is 0. If it is, then we can just easily do some math because we know the minimum bound, and we can just return the minimum sample rate. If the potentiometer reading instead is 1023, or the highest it can be, then all we have to do is simple math and return the period for the maximum sample rate. But if it's somewhere in between, then this code down below that runs. And what I basically do is a linear function between our minimum and our maximum sample frequency. Lastly, there's the Oscope Read function that I've written. In this Oscope Read function, all this is designed to do is check the reading on the oscilloscope, reset the timer, then all it does is it prints the Oscope reading. All of those spikes come from the odd symmetry version Fourier series. This square wave, when it's then broke down into its Fourier transform, you get a spike at 10 hertz. Then you get another one that's at one of the harmonics, and another one at the harmonic, and another one at a harmonic, and another one at a harmonic. Each one of these represents the portion of that frequency that was used to create this square wave. For the triangle wave portion, we also see each of those little terms as harmonics. One right here, one right here, one here, and one here. You can see those are our components of the Fourier transform. Thanks for watching. I hope you enjoyed.